Okay, thanks. So yeah, I'm the other piece of bread in the Nottingham sandwich. I don't know who's the top one or the bottom one. Yeah, this talk will be quite different from what you've heard so far, but I make no apology for it because it does have some maths in, and here we are at the INA. So, there's various people I've talked to about this over the years. Tom about 5 years ago, so he's probably forgotten it, and Karthik a bit more recently, but most of this is my own sort of errors and work. So I'll first of all explain, what's all this about, you might be wondering, give some examples, talk about something called scale invariance and the EM algorithm, which you might also be wondering what on earth this is, and then have some conclusions. So first of all, let me motivate what on earth this is all about. If you go back to the pandemic, then here's something we've already talked about, the R number, which is very popular in the sort of UK media and all over the world, and how was the R number calculated in practice? So we all now know something about this. There's different models, different estimates. You put them together and derive a consensus in some sort of manner. And models that were used to do this would have often different assumptions. They may have slightly different data, and the models may even have a different view of what R actually was. So that's another issue. But nevertheless, they all provide estimates of R. And you might ask yourself, how different might these estimates be if you have these sort of different models at play? So this and other things I've seen over the years have sort of motivated me to think a little bit about the following sort of broad question, which is this. Suppose you've got two models, and both of them contain some parameter or parameters which are supposed to represent the same thing in real life. I'm not claiming that R is a real life quantity, by the way, but there are such things that you might think of as something you can measure in real life. And then these two models are both fitted to the same observed data. So different models, same data. And then the theoretical question I think is interesting, is to say how different could the estimates be in this situation. So it's sort of stepping back a bit and saying, well, okay, model comparison is one thing, like two kinds of models, how do they behave? And this is to say, well, what if you're doing estimation based on those models, what's going to happen then? So that's the sort of broad picture. The answer to this is I don't really know, but I'm going to sort of show you a few things as we go along. You might wonder why bother doing this, and there's three good reasons. So the first one is the key one, is if one of the models is much, much easier to fit to data than the other, then if you can show that the estimates should be about the same, then you've made a huge gain, right? So it's trying to give some theoretical justification. The other one is sort of waffly, well, it provides some insight and it's, adds to the tree of knowledge and all this sort of thing. And the third reason is that you don't need a reason. Okay, just as an aside, so we've already seen, discussed at this meeting a number of occasions, the point that there's lots of examples in the literature where you have a very complex, well, in fact, I just had a talk about this, have a very complex model and you try to approximate it with a simpler one. And there's often theoretical results which exist which sort of justify the fact that the models themselves may, converge or you get better agreement or something like that. But what's not so clear in the literature, at least from what I've seen, is that, just because the models happen to be similar doesn't mean that the estimates are, right? So I imagine you could construct very sort of weird examples where the estimation is terrible, but the models look very similar. All right, so this is the kind of idea that I have in mind to think about. Okay, if you want to make this question more precise, you've got to start making some choices, and here, there's as many as you like. So what kind of models do you want to compare? What kind of data, because that's going to influence the sort of things you want to look at in real life, and also what kind of estimation. So you can all choose your favorite three of these and then go away and work on it for 5 years and come back at the next meeting and tell me what the answer is. Okay. So here I'm just going to focus on something a bit more specific. Those of you who know me will know that I'm always sort of Bayesian and MCMC and all that kind of stuff. Neither will feature in this talk, surprisingly. So I'm going to talk about maximum likelihood. So let's hear it for good old MLEs. I'm going to think about density-dependent Markov processes. Why is that? That's because these are processes which have limits, which are deterministic ODE models. And I'm going to throw in some noise, for reasons you'll see why in a minute. And the particular data setting I'm going to think about, and here's some notation you might need to remember as we go along, is that we have observations sort of discretely, so not continuously, just sort of at some intervals. TK is the time that we observe the process, and XK is the value of the process. So here, we're assuming that we completely observe everything, but not all the time. Okay? So that's the setting. And of course, as I say, you can make up your own sort of what kind of data do you want, but this is what I'm going to start with. Okay, density-dependent Markov processes. If you know what they are, you've seen all this before. If you don't, the short answer is they are Markov processes, so continuous time Markov chains in d dimensions. D will always be 1 in this talk. And the idea is that there's some notion of the population size which you can change, and as you do that, you get a sequence of processes, and the state space will then change from being, say, the integer lattice with m is 1, that's the original process, to chopping it up into finer and finer pieces, okay? So instead of sort of going from 0, 1, 2, 3, you go from 0 to a half, to 1, to 1.5, and so on, if m was 2. And the transitions have to satisfy a particular property. But the reason that we care about these processes, and this is well known back into the sort of early 1970s, is that under suitable conditions, a sequence of stochastic processes converge to a sort of ODE limit. So this is all terribly well known, and it's often used a lot in sort of academic modeling as well. Okay, this is all very, very simple mathematics in this talk, you'll be pleased to know. So here's an example of such a thing, a Poisson process. Here I'm thinking of a Poisson process as something which counts the number of events that you've seen. So I'm not thinking of it as a point process particularly, but how many events have you seen up to a point in time? So it could be 0, 1, 2, 3, and so on. You go up one event at a time from k to k plus 1. This happens at rate lambda. If you look at the m-scaled process, so now you chop up the state space, so it's now 0, 1 over m, 2 over m, and so on. You still get transitions from one state to another adjacently, but you now, to keep lambda having the same physical meaning, you now have to say, right, you've got to move m times faster. Okay, so there's a sort of relationship there. And the ODE limit is this one, dx dt is lambda, all right? So this is probably the least complicated ODE model you'll see all week, but here it is. So what about this? So that's, you have this class of models which are density-dependent Markov processes. What do I mean by an ODE model plus Poisson noise? So this is something that's very common in, for example, infectious disease modeling literature, and I think elsewhere, which is the following. So you've got your data look like this, so observed value at this time for a number of points. The ODE model is this one, and what this assumes is that because even deterministic modelers realize that life isn't deterministic, so you have to have some kind of noise or some sort of error or something like that, and maybe get a likelihood. And one way to do this, which I say is quite common, is that you assume that the kth observation is actually drawn from a Poisson distribution, and the mean or parameter of that is the solution of this ODE model. Okay, so as I say, this is very common. You'll see lots of papers that do this sort of thing in the literature. Okay, so let me show you now the kind of thing that you might end up doing. So here's some data. So here's time, 0, t1, t2 up to tn. Here are some observations, x1, x2, and I'm going to think about a Poisson process. So this is the number of events you've seen so far. So these values are going up, right? They're not allowed to go down, otherwise it's a very silly model. Okay. Imagine you have two modelers, deterministic modeler, stochastic modeler, same data set. Off you go, you're going to fit your model and say, how different can the answers be? And what do we mean by answers? We want to estimate the rate at which these events occur. So if you are the stochastic modeler, you say, I have my Poisson process. If you've ever done a course on these things, then you'll know that it's possible to sort of write down a likelihood of observing that your process at time tk is at value xk for all these values. We're starting at t0 is 0. You get a likelihood, it depends on lambda, that's the rate of events. You can get this product form, and it's tractable because we actually can write down an equation for what these probabilities are. Okay, so far so good. And if you solve it, then here's the answer. So this is lambda s is the stochastic maximum likelihood estimate. And you'll notice it actually only depends on the total number of events divided by the total length of time. Right? So if you've seen this stuff before, it's all like, yeah, no big deal. If you do the same thing for the ODE model, then what happens? Well, the answer is, first of all, I have the Poissonized likelihood, which is a product of Poissons. By the way, one thing I've noticed as I've gone along in this is I increasingly think this is a really dumb model, but so apologies if you've used it yourself. And it's really because of this independence property, you know. So I mean, I know people do more sophisticated things, but you do see this. Anyway, I digress. So we multiply these things together. Again, it's tractable. Why is that? Well, partly because I know what a Poisson mass function is, but also because I happen to know what xt of k is in this particular case. All right. And here's what you get. So this time it actually depends on all of the observations and the sum of the times like this. And guess what? It's not necessarily the same. So even in this incredibly simple, basic model, with these two modelers who are, you know, completely different in their view of life, you end up with this. So you could say, well, right, how different could it be? All right. So you do a bit of calculus, and the answer is, if you fix xn and tn, so that means we're just fixing one of these things and varying it with the other, so that lambda s was the ratio of these, it can be very different, like very different. N is the number of observations here. Here are the two extreme cases. So this is the point that's fixed. This one says nothing happened for ages, then there was like a whole bunch of events here, and then, you know, this here, and the other one says, okay, nothing, you know, all these events happened pretty much immediately. So one of these, if you imagine fitting a straight line, it's going to be very low down, that's this one, and this one is going to have a very high gradient, which is this one. Okay, so again, it's sort of no big deal other than to say you can put some bounds, things are very different, yeah, we probably could guess that anyway. The thing that interested me was this, which again isn't that much of a big deal if you think about it, is that suppose there is a theta such that theta tk is xk, that means you can actually draw a straight line. So this is the solution of the ODE model here, and say suppose there was a value such that all of the data lie on this line, then in fact you get the same answer. So it's exactly the same thing. So this immediately suggests some kind of heuristic, which is to do with the fact that, well, if your deterministic model has looks pretty much like the data, maybe the estimate isn't all that bad. Okay, so at least this is something we can say explicitly here. So next question is this the only process for which this is true? Okay, you might think, yeah, this is all very simple, and surely anything more complicated, it's not going to work. So you start going through the sort of cookbook of elementary stochastic processes. So the next one on your list is the linear birth process. So it's a model in which individuals give birth, never die. Here's the state space. Basically, you go from state k to k plus 1 at rate lambda k. So lambda's a sort of per individual birth rate. This is density dependent. The ODE limit is this one. dx dt is lambda x, so the solution looks like this one. And again, if this time you can't write down what the MLE for the stochastic process is explicitly, unless the observations are equally spaced, in which you can. But in general, it satisfies this. This is what statisticians call a score equation. It's the derivative of the log likelihood equated to 0. So you can show that, okay, the MLE satisfies this, so put lambda equals lambda s, and this will be solved, where s here is the time between events. It's this thing here. On the other hand, if you do the same thing for the deterministic process, or the Poissonized likelihood in this case, what happens is that you have a different equation which is satisfied, but guess what? You can show that if the data lie on the solution of the ODE model, then in fact these are the same. Okay, and this one is perhaps, at least to me, a bit less obvious. So, if I were to ask you, do you think this is going to be true? You think, well, maybe it is, maybe it isn't. It's not, it's non-linear now in terms of its exponential growth. So maybe it's not quite so clear. Linear death. Okay, this is a process where you die linearly instead of being born linearly. You have a different state space. This time it's restricted. Same kind of thing. Again, it's density dependent. It's a parameter called mu. And the story is the same. So once again, the MLEs are solutions of explicit equations, and they agree if they lie on the solution of the ODE model. Right? And all of these things you can sort of show analytically. Right? Okay, next one. So this is now where it vaguely relates to epidemics, because if it's an early stage of an epidemic, you might use a branching process approximations. Here's a linear birth-death process. That's this kind of thing. Now you have births happening and deaths, births at rate lambda per individual, deaths at rate mu. It's density dependent. And oh, now here's something. Here's the ODE limit, lambda minus mu times x dx dt. Here's the solution of that equation. And one thing you will immediately notice is the following. I'll come back to this. Is that in the ODE limit, there's now only one parameter. Okay, so here's a sort of slight little difference as you go along in your optimistic mood, if this is all going to work. You discover that there's an extra complication here. So For the stochastic process, yes, there are formulae out there in literature where you can write this down. It's a very, very complicated sum. I mean, it's easy to code up, but nevertheless, it exists. MLEs exist for lambda and mu, but for the deterministic model with a Poissonized thing for the noise, then you only have an MLE for this. Okay, if the data observations are equally spaced, so if we go to that particular special case, which in infectious diseases may not be that unrealistic, like you have weekly data on cases, for example, or whatever it is, then if you look in Niels Keiding's paper in Annals of Statistics in 1975, you'll find an explicit formula for this rho. So this is like the growth rate lambda minus mu for the stochastic model. And you can also show that, or I can show, that if the data lie on the ODE model, then again, you have this agreement. And what I can't yet prove, but I hope is true, is that this also holds if you have non-equal observations. But it's, you know, technically it looks like a bit of a nightmare, but well, we'll see. Maybe next week I'll do it. Okay, something very quick. So let me talk about something called scale invariance. So this is so far relating to deterministic and stochastic models, but along the way, I kind of realized that there's more you can say about stochastic models in the following sense. So if you think about what's going on in these processes, so one way to relate the model, stochastic model with the ODE limit is to consider a sequence of m-scale processes. So what's happening is that the state space gets finer and finer as you increase m. You're introducing more and more sort of points that you can move, and in the limit, it's like you end up in the kind of the ODE state space, which is continuous. So that's a natural way to think about relating these things together. So if you go back to the Poisson process, so recall that we had this MLE. So you can show relatively easily that this has what I call a scale invariance property. So this is the MLE we're talking about, not the process, which says that if the state space is scaled by a factor m, actually the MLE doesn't change. All right, so, and this somehow is beginning to sort of forge connections between the stochastic world and the deterministic world. Let me show you visually what that looks like. So here's the original state space, 1, 2, 3, 4, and so on. If I double it, so m equals 2, so I've got half, 1, 1.5, 2, and so on, but I observe the same data and then fit the model and say, what do I think lambda is for the MLE? It turns out it's the same thing. And this would be true for any m. So if you think about this, you can do the following. So given your observed data, you can get a sequence of MLEs for the m-scale process. So every element of this sequence would be identical if you have this scale invariance. If you didn't, you just get different MLEs, but that's fine. If you then take the MLEs, so these are estimates, you put them back into the stochastic models, that gives you a sequence of processes. And what do we know about this from density dependence? We know that they converge to an ODE limit. So what you would imagine, and I haven't rigorously proved this, although I can't imagine it isn't true, is that if the data happen to lie on the ODE model, then this sequence of MLEs put back into the stochastic model is going to converge to an ODE model with the same parameter. Okay, so there's quite a few things going on here, but you've got MLEs for the stochastic model, put them back in, you get an ODE limit, and the claim here, or my suspicion is, that's the same model that you would get in the sort of Poissonized version of the ODE. You can also show scale invariance holds for MLEs for linear birth processes, linear death processes, and linear birth-death processes with equally spaced observations. I should say this is maybe not entirely obvious, again, that you might think, if I just double the state space, would I get the same estimate? You know, what's going on there? I'll try to be very brief about this, that you, as well as proving things directly using some of these equations, which you can write down, it's also possible to prove some of the scale invariance using the EM algorithm, which seems a bit weird, but let me just briefly explain how it works. So if you the linear birth process, imagine this. So what the EM algorithm does, it says if I have discretely observed observations, I want to take a maximum likelihood estimate. One way to do it is to do data augmentation in the bits I don't observe, conditional on what I do observe, and then you kind of iterate back between maximizing based on your augmented data, and then you update your augmented data by taking the average given the current value of the parameter, and you go backwards and forwards like this. Now, for example, if you do this for linear birth, and if you just look at one interval to keep things simple, you observe x0, xt, the number of births is b, which is this, which you actually know from the data, so you observe it in this process. If you also observe the process continuously, then the MLE is of this form. So if you've seen this before, fine. If not, well, here it is. Just a formula which says you can do this. If you now were to scale, sorry, this is just a description of the EM algorithm. So you initialize at some point, and what you do is you then compute the value of the unobserved process conditional on the start and end point and the current value of the lambda that you've got, and then you set your next guess using the MLE formula, which is this one here, and the sequence is known to converge. So if you do this for the M-scale process, then what happens is that instead of B, you have MB. So it's just like, if you used to go from 1 to 2 to 3, now go from 2 to 4 to 6 if M was 2. So this is just multiplied by M. And if it turns out that, now you should have a look at this because it's nearly coffee time and you need to just be awake. If you have a look at this, this says what's the value of the M-scale process given the start and the finish and the parameter, and what if that was the same as M times the original process, x1, given the start and the end and the parameter. Now, if there wasn't the end point here, anyone who knows about these processes will say, well, if you have birth process with 2 individuals, it's the same as 2 processes with 1, and you just add them together, so the expectations scale. And this is saying, well, what if it was true even if you conditioned on the end point, which is far from obvious. But if it was true, then what would happen is that you imagine you now have 2 EM algorithms, one for the original process, the other for an M-scale process, the same lambda 0, then they would have the same processes. So basically in this formula here, sorry, not that one. Yeah, this formula here, this would be B times M, and this would be something times M as well, so it would just cancel out. Okay. And it turns out that it's true. So for the linear birth process, you can actually prove that this is the case. And it's also true for the Poisson process and the linear death process, but not the linear birth-death process. You can prove this algebraically. It's a bit of a mess. There's also some very nice probabilistic proofs, which time does not allow me to go into, but you can also do it for that as well. So this is just to say it gives you another way of proving or trying to attack these problems. Okay, conclusions. So I suppose the main thing that is maybe is of interest is that it kind of suggests that there might be some heuristic out there, which obviously is an enormous amount more work, which is this, that if your data are well represented by an ODE model, then maybe fitting that with this sort of Poissonized noise might give you a pretty good approximation to what you would get if you fitted the stochastic model. That's the first thing. You might be wondering about epidemics, because as we're at an epidemics meeting, I should probably mention them. So if you do this for an SIR model, scale invariance appears to apply in some special cases, but not generally. So yes, if the data specify exactly what events have happened in a time interval, then you do get scale invariance, but you don't otherwise. But I mention this because you might be thinking, does a non-linear process like an epidemic screw everything up? And the answer is it seems to be a bit more going on than that. Okay. And the final thing, so this is the last slide, what if you do something else like least squares or method of moments or your favorite estimation, Bayesian stuff? The answer is yes, you can do those things. I've looked at some bits of some of them. So for example, least squares, you get some very similar looking results. So it's not just all about maximum likelihood either. That's it. Thank you very much.
Time for a question or two.
So I think with the Poisson one, the normal argument is, say you've got 500,000 new infections this week, and you've detected 500 of them. Those 500 are going to be the correction between that, doing that 500,000 stochastically and doing it by an ODE, but then you're sampling 0.1% in whatever surveillance you've got, is going to be almost nothing. So I think that's the normal argument people have for Poisson. But I think equally, COVID was unusual, and we saw an unusually large number of infections in the data, so I think that argument probably failed, and it's probably quite important to see how to push it. But I think my question would be, isn't there a slightly stronger version of Poissonized ODEs that's where those limits are quite well controlled?
Yeah. I mean, as I said, you can make any choice you like about how you want to add some noise to your stochastic model, and this is just one way of doing it, but there's others as well, definitely. Yeah.
Oh yeah, I might be asking a question through ignorance, but I'll do whatever. So my question is, when you gave kind of case examples of ODEs where they may not work unless they look a lot like the data, they're all examples where there's things like cumulative cases, where there was clearly dependence between the data points. So, you know, they weren't cases, so they're like, I think prevalence rather incidence and cumulative cases, where you really shouldn't be using, I think, a Poisson error, because conditional on where the model is, it actually matters what the last data point.
Oh yeah, no, absolutely,
So
no. I'm not.
yeah.
I'm not particularly justifying, you know, saying one should always use Poisson noise. I'm just saying that, you know, it's a way of adding some noise to a model as a starting point, and you could look at other mechanisms for doing that and ask the similar question of, you know, how different could the estimates be?
So I guess what I'm trying to work out is that why they're falling down in some cases, because they've kind of been set up to fail a bit, maybe, or is it, or are there other factors going on? You know, when you're saying you Poissonize the Poisson process, is that why it's maybe failing? Or,
By failing, you mean,
or, you know,
you mean getting different estimates?
There are examples where you had very, very poor estimates.
Oh, okay, yeah.
You know.
No, I think that just has to do with how representative the ODE model is of the data, sort of regardless of the noise. I think, yes. But perhaps another comment I should say is that this sort of link between saying, oh, if the data lie on the deterministic model, you get the same answer. Yeah. I mean, that's not necessary. Okay, so even in the Poisson case, you can come up with examples where, you know, there are discrepancies, but you still get the same estimate. Okay. So there's a whole thing of like, how do you, you know, put together find a way of talking about the difference between the observed data and the deterministic model, which then sort of tells you something about the estimation. Yeah.
I was wondering, have you looked at differences in distribution parameters, so confidence regions or KL?
Oh, no. I mean, okay, one obvious thing I should say about this is that, sorry, yeah, the question was to do with like looking at confidence intervals. So yeah, obviously I'm just looking at point estimates, and yeah, even I realise that as you sort of, you know, change, for example, the scale of the data and like the M process, you know, the estimates would change as far as the variability goes. So, for example, if you do a Bayesian version of this and say, okay, I'm going to have conjugate priors and I get gamma distribution for my birth parameter or whatever it is, or event rate in a Poisson process, then yeah, you'll get different distributions with different variance as you do the M scaling. So this is really a very simplistic thing, which just says, you know, I've got these two sets of modelers, stochastic, deterministic. You know, the policymakers want one number, which is your best guess for the M, you know, the R or whatever it is. You know, what is it? How different could it be?
Last question from me, if I may. Do you have a conjecture for which way the discrepancy goes as the variance increases?
No.
Yeah. That's not obvious.
No, it's not. No, I think I wouldn't say none of this is obvious, but I think, yeah, a lot of it. Yeah, there seems to be a lot more going on behind the scenes. So yeah, it's not terribly obvious. Yeah. Yeah.
Great, thanks very much, Phil. So time for afternoon tea now, and lots of discussion out in the foyer, I hope.
Yeah.
Okay. Thanks, Phil.